Okay, so welcome back. We're still here in chapter 3. Okay, it's a very dense chapter, and the last topic that we were subtopic that we were discussing was about categorical feature engineering.
Mhm.
Okay, those data types that have labels or as the author describe them levels. In R, the factors are composed of levels. We talk about lumping, another word that you could find for uh, condensing those grouping those levels that have small observations. You could find them as also as merging those labels or levels that are infrequent. Then we talk about one-hot encoding and double encoding and the differences. Uh, Make sure that you don't have that many. It doesn't explode into that many uh, features, okay, because that's one of the drawbacks of the one hot encoding and dummy encoding. But uh, if it's reasonable, the number of variables that you're going to be getting from that encoding, so it's the go method. Then we have label encoding, which is assigning it's a numeric conversion for those categorical variable levels. And one of the caveats of that method is that it basically orders the levels. So if you don't have an explicit um, order of those levels, then it should not be used. Okay, it's morely for ordinal type of categorical labels. If you are nominal, then you should go one hot on dummy encoding or other methods that we're going to be discussing. Okay, so I believe this is the last subtopic from the categorical encodings, and the subtopic is titled alternatives. So here, the author explores other alternatives apart from the one hot, from the label, from the lumping, merging, and he discusses two uh, methods that uses the target, okay, uses the response variable to create like a mean statistic for each of the labels or a proportion. Okay, so if the target label is numeric, you could encode it using the script that you have right there in your screen. You can encode, for example, the neighborhood that we've been using as an example in the AIMS data set. You can generate from each of the neighbors, you can generate the average sale price. The sale price is the target, the response variable. You can create an average, okay, and then assign that average to each of the levels of the neighborhood. And you can use then that mean or average sale price as a type of encoding, okay, instead of the label. But of course, there's no free lunch, right? One of the problems that the author tell us is that it can create in your test data, it can create some data leakage because you're using information from the train data set and then using it for the test data set. Another drawback is that usually in the test data set, new data, for example, that is coming from the pipeline, sometimes the result, the target variable is not known. Okay, so if you are going to do a prediction without the target, values known in that new data, then this method is not going to be available to you. So the other alternative that you can use is the proportion. Okay, so in other words, we're going to, instead of calculating the a mean or a median or a statistic from the target label, what we're going to use is not the target label, but the counts, okay, of each of those levels in that categorical variable or column. And what we're going to use is do a proportion. In other words, how many counts divided by the total counts of the whole, categorical variable. Okay, so here you're going to use the counts and then the total of the counts, right? And it's going to give you a numeric value, and that numeric value then you can use it for assigning that numerical value to the specific level that you are trying to encode. Okay, so to give you some directions on where you can find other type of encodings, there are several. In the tidy models, there's a package called embed, and in embed you can see other type of encodings. For example, weight of evidence. You can use also length codes, hashing also. So there's plenty to choose. But one of the things that you should be aware is that if you're using target encoding, beware of the data leakage issues, because you're using that target, and also it's going to create also kind of a correlation to that categorical variable, because you are using another feature. Okay, so basically that it is. There any comment so far?
No, I don't have any comments, but the thing is that this one is one of the least intuitive for me to understand, because
Right.
yeah, it is about the why we have to transform the proportions, or like getting the average price to categorize or encoding this kind of neighborhood value. So it is not that intuitive at all.
Correct.
So, and also
yeah,
it's too many higher risk of the data leakage problem also gonna be concerned. Yeah.
Right. So just two comments. For example, in this data set, we're taking the neighborhood, right, as an example, and the neighborhood is not that bad. Okay, it has around 28 levels. If you lump it, you can reduce it to 22, and that's not that's not bad for one-hot encoding or dumb encoding. But take the zip codes, for example. The zip codes really are categorical. They're not numerical, because there is no there is no arithmetic function that is going to give you some value if you subtract or add or divide zip codes. So what happens is that, let's say that you have 1,000 zip codes. So if you one-hot or domain code, they're going to have basically 1,000 additional columns. So that's not a method that you should you should approach. Then if you do label encoding, then the problem is that zip codes are not ordinal; they are nominal, categorical types. So label encoding is not going to it's not going to encode it appropriately. So you have to use any other method to try to convert those labels, those zip codes, into a numeric type, okay, for your machine learning. And usually you can use this type of methods. Okay, also hashing, it can be used. I'm not going to discuss it here, but in the embed package you can see other alternatives on how to build with them. And sometimes you have to experiment. Okay, you have to use different, different approaches to see which is the approach that really works best for your model. Okay, we're good.
Okay.
Okay, so let's go on. Let's keep going. Okay, so in this subtopic, the author just mentions this. Okay, it doesn't go any, it doesn't gives you any examples or anything. But this is more a dimension reduction technique for your features, different from the filter selection, right? From the feature selection, what this calls filter methods, etc. This one uses all the space, right? Or all the variables, the predictors that you're going to be using, but then rearranges mathematically in a format that then you can reduce the the number of useful predictors. The method that usually is the traditional method for dimension reduction is PCA, okay, principal component analysis. And what it does is that it rearranges those variables, okay, uncorrelated them, and then the first principal components that that result from that rearrangement. What it does is that the first principal component is going to have the most variance, okay, from those predictors. Then the second is going to have the second most variance, the third, etc. So what you're doing is that you're grouping the variance, the information that is going to help you for your, for your model. You're grouping it in a less number of components, okay? But we're not going to be, discussing that. That's going to be a topic, a whole topic for chapter 17, all right? But a big difference is that dimension reduction uses all the information. When we do feature selection, we are trying to discard the variables that have or no information or very little information that is going to help our model. With dimension reduction, we're using all, but then we're grouping it in a way that we get the most variance in a less number of variables or components. Okay. Okay, so that's basically what I have for the dimension reduction, right? Then the author talks about the proper implementation of this, this feature engineering process. And one of the things that you have to be aware is that these methods that we have discussed, they usually have an order, okay, in terms of how you should, do the first, the second, and the third in order to appropriately convert your data into a machine learning model, understandable data set, okay? And this order can change depending on your data set. So for example, the suggested way that the tidy models framework says that we should approach this is that we're going to first filter those 0 or near 0 variance features first, then perform any imputation that is required. Normalize your numeric features so that you don't have that skewness, that skewness present in your models, especially if you are doing the ordinary linear regression or logistic regression, etc. Then you standardize your numeric features. Optionally, you can perform your PCA if you have a lot of features. Okay, I'm talking about, let's say 200, 300, etc. Variables, and after that you're going to one-hot domain coding. Depending on your case, maybe what you're going to do is that after the one-hot encoding, then you're going to perform the zero or near zero variance. Because remember, when you explode that categorical variable, sometimes if you don't do a lumping, a merging, then some of those levels that are going to be converted as variables, they have little information. So sometimes the zero variance, you can do it at the beginning, at the end, or both. Okay. And PCA is going to be something that is going to be kind of an optional. Also the imputation, if it's required. All right. Okay. So, okay. The author mentions one of the, one of the issues that we have when we are performing, the machine learning pipeline is that we should be aware of what is called data leakage. And usually data leakage is defined as information that is contained in the training data set that then is used as part of your unknown data. Okay. So for example, let's take imputation. Okay. Let's say that when you impute a variable by the mean, okay, you're going to calculate the mean for the known values, and then you're going to apply it to the missing values. If you use it on the whole data set and then split the data set and do your machine learning, you are incorporating in the test data set, which is the known data, you're incorporating information from the training set. Okay. The right approach would be to calculate, impute the training set first, okay, with that information, and then apply that mean that you took from the training set, apply it to the missing values in the test data set. Mm-hmm. Why? Because then you're applying the information that you gathered from the training data set, which is your model parameters, then you're applying to unknown data. Okay, so instead of using the whole mean for the whole data set, we're going to use for the training set and then apply it to the test set. The good thing is that, for example, the tidy models framework incorporates these techniques. Okay, so for example, in the tidy models, when you use the training set for your recipes, okay, which are the transformation that we're talking about, each recipe is applied to each resample. When you use the cross-validation, it's applied to each resample, okay, what is called the pre-process here, mm-hmm. Okay, and then it's applied to the training set, that chunk of the training set, and then is evaluated with the validation set, okay, that portion of the training set that is reserved for the training to avoid overfitting. And this process repeats for each of the folds. Okay, so we have encapsulated here, we have a model that is going to avoid, okay, that problem of data leakage, of information passing from the training set to the test data set, in a hazardous way. Okay. We're going to talk more about that because this is one of the examples of data leakage. There's others that it can be, you have to be aware of it to make sure that your model follows the best practices of a machine learning model. Okay. Okay, and that's one of the reasons why that pre-process has to be done, through the training sets, to the folds in a systematic manner, in order for that test data set to be insulated from the, from the model. Okay. Any questions?
No, I'm good.
You're good? Okay. Mm-hmm. Okay, so this is an example, again, using the games, our toy data set, in putting the pieces together. And this is an example of the order and what kind of pre-processes methods can we use. So for example, we can create, using the tidy models example, you can create a recipe where we include this feature engineering methods. The near zero variance for categorical variables, ordinal encode for the ordinal, central escape normalization, standardize all numeric features, and then one-hot encoding. Okay, so this is an example, right? Then this, what is called a blueprint, right? Recipe object. Then we're going to be applying it to, okay, this is the bake. This is how it looks, right? It's going to explode the data set. When you apply the recipe, when you prep it and bake it, it's going to explode it to 220 new features. Okay, after all that, feature engineering. Then what we're going to do is that we're going to apply it to the resampling, right, method. This time using the Caret, package. Okay, because you can use some of the functions from the tidy models. You can use it in the Caret. Is the the same developer, Max Kuhn. So we're going to use cross-validation, right? The number of folds is going to be 10, and we're going to be doing a repetition, to get more data. We're going to construct a hyperparameter, okay, which is because we're using KNN, K nearest neighborhoods. The only parameter that you can, tune is K, the number of neighbors. Then we're going to do a fitting, right, with our blueprint, with our pre-processing to the training set. Okay, the methodology is going to be KNN. This is going to be the cross-validation plan with the hypergrid, and the metric that we're trying to minimize is the RMSE. Okay, and we're going to, be during the other discussion of the algorithms, we're going to be seeing this more frequent. So we already have our cross-validation plan, our hyperparameter instruction, and then we're going to tune it, and this is going to be the result. Okay, so the result, which is encapsulated here in KNN underscore fit2, this is the model. Okay, and because we're doing a hyperparameter tuning, we're trying to see which is the optimal K according to the RMSE, and what we're trying to do is minimize. And Keuntae, you're correct. K10 is the one that has the minimum RMSE. So that points that with K10, we have, with that recipe, we have, the optimum model. And if we plot it, right? If we plot it, we'll see that K10 is the minimum, right? The minimum value for RMSE. All right. So basically, this tells you the importance, right, of the feature engineering, and you can experiment. You can try to see, okay, if I encode the categorical values differently, how will my model, will react, right? Okay. So basically, that's chapter 3.
Okay.
We made it.
Yeah, that's nice. Yeah, thank you for your very clear explanation and everything. And then, yeah, it was very helpful. And then also, yeah, it is very, very, very hard and important chapter. Yeah, maybe I think we have to keep in mind about these chapters too. Because later in the rest of the chapter, throughout the rest of the chapter, maybe we might keep revisiting that chapter again and again and again for the data processing purposes. So
definitively, this is a chapter that you have to go back and also try to find more information about the things that the author didn't cover. Okay, especially dimension reduction. Although it's in chapter 17, but it's a technique that you should be aware, because it's common. It's used very, very commonly. All right.
Okay. So So thank you. And then now let's move to the chapter 4. Because now basic things but very fundamental principle of the machine learning things are done. Because chapter 1 through 3 is 1, 2, 3 is a kind of like a very, very critical and very fundamental principle of the machine learning process. So now we, from chapter 4 to chapter 22, which is the last of the chapter, we're gonna try to look at the more specific techniques for the machine learning. So depending on our data structure, or depending on our research questions, or depending on our hypothesis and objective of our research. So the most simplest thing for the machine learning is the linear regression. So in the chapter 4, this book actually deals with how we can conduct the linear regression for the machine learning purposes. So learning objectives is we're gonna try to study like a simple and multiple linear regressions, and then we're gonna how we can do the model assessment, and then principal component regression. This is actually kind of what we just covered about the data dimension reduction process. If we have too many features in our data set, maybe we can reduce their dimension, and then using that principal components as instead in our regression to figure out the relationships or some kind of predict some of the outcomes. And then there is also regression called partial least square regressions. And then final one is feature interpretation. So let's get started. So here is just kind of a requisite kind of thing. So about what kind of packages we're gonna cover in this chapter, like DPLI-R is just kind of a tidyverse for the data manipulation process, right? And then also we're gonna try to do that for the ggplot, like some visualization and Carrot for the cross validation. And also we're gonna use the VIP, because Carrot and VIP gonna be used about the maybe later part of this chapter to further some kind of a model assessment, and then some kind of identifying the variable that are very important to predict our outcome variable. So those are the things. And then, so simple linear regression. So actually this chapter actually have a lot of some kind of mathematical formulas. So I'm gonna try to explain as easily as possible so that we can understand. So simple linear regressions is just kind of a very statistical relationship between just two continuous variables. So if we have a kind of a x variable like this, and then there is a y variable as an outcomes, and then maybe there is x1 and x2 and then xi, and then there is also y1 and y2 yi. Actually, when we try to do this kind of analysis, we actually assume that x to the y is the 101, like you know, 101 correlations. So x1 gonna be correspond to the y1, and x2 corresponds to the y2, and then xi is correspond to the yi. So based on these kind of relationship, we actually have some of the average kind of a relationship throughout these kind of things. So that's the actually kind of what is called a beta I, usually. Maybe in this case, yeah, it's a xi kind of thing, but beta 1 kind of thing, because it's only x1 and y1 kind of relationships. So basic, just kind of general formula of this one is this simple linear regression is the yi equals beta 0, which is the constant in y-intercept. And then beta 1 is the regression coefficients that represents the relationship between the x and y, right? So it is actually called the rate of change. And then EI is actually not the EI, it's the epsilon I is the error term. Because the reason why we have this kind of error term is even if, like for example, if we have if we draw some kind of scatter plot, and then if we have these kind of relationships, and then maybe we can draw some of the regression line that minimize the error term, right? And then that's the kind of things. Maybe this is because of all of the reason why we can actually call the regression means actually all of these kind of actual observation values actually returning back to the predictive value along this line. That's what we actually call the regression. So it is actually like returning back, kind of going back to the predictive value along the line, depending on these kind of observations. That's the regression. Actually, the word regression means like going back to the some hypothetical predictive value. So due to those kind of things, there is always have some potential error terms like this. This is epsilon, right? But what is the problem right now is that throughout these kind of when we looking at these kind of a scatter plot, there might be a lot of potential lines like this, right? But among these of the lines, what we can have to find is what's the only line that actually minimize error term, like a residual error. So that line gonna be have only one line among the whole potential line that represents the relationship between the x and y. Because the reason why we can have a lot of line means because we have a lot of different observation, and then based on that observation as a only single point as an observations, we can actually draw a lot of potential lines, regression lines, based on this kind of a scatter plot. But the thing is, what we wanted to find is that there is only one line that minimizes the error term. That's the basic formula of these linear regressions. So, and also when we try to do the simple linear regressions, we actually assume that the error term is normally distributed, which is the mean of the zero. So that means maybe, for example, there is a regression line, and then maybe if we have this kind of you know, these kind of observation points, and then we can actually, when we returning back to all of these value into along the line, there is actually error term happens. This is epsilon 1, epsilon 0, epsilon 2, epsilon 3, epsilon 4, etc. So when we sum of all of these things, like sigma I equal 1 through n, and then epsilon I, this one is actually 0 or close to 0. But we in the regressions, we actually assume that this error term, the sum of the error term should be 0, right? But the thing is, when we try to calculate about the square root, like a square, not the square root, like a power by 2, and then we can, when we try to average them, this one actually gives us about the sigma square. right? That's the actually, this one actually called the variance, right? So in the linear regressions, we actually assume that if, error is the normally distributed and then highly random. That's the basic assumption of the linear regressions. And then when we move down here, so our next question gonna be, okay, let's say we have a kind of some of the single linear regression equations. So that means how we can estimate the y values by using those kind of relationships. So that means we to predict the more accurate predict value of the y, we have to find the best fitting line, right? Actually, the best fitting line can be found by minimizing the residual sum of the squares, which is the RSS, right? So this is the kind of things. So when we're looking at this one, is yi is actually actual observation, right? But this one is actually what we call the y hat I, which is the predictive value. So when we try to so yi minus y hat I actually kind of a what is called the error term, right? So when we square it and then when we sum of the all of these, we need our goal in this is we had to try to find what's the minimum value for this. What is the beta 0 and beta 1 that minimize this kind of error term? That's the regression model we need to find. And then that's the best fitting line that minimize the residual sum of the square errors. So in here, in example, so when we try to using the AMS housing, and then we can actually split those data set by use the training and testing data set, right? And then by using the trained data set, we can try to develop the very one single linear regressions between the sales price as an outcome, and then the ground living area is the one critical independent variable like predictors. And then when we summarize the model, we will get these kind of relationships. So in the inferential statistic purposes, we can actually found that the kind of residual is the minimum is like this, and then the maximum is like this, and then the median value is like this. And then I think that this one has a residual standard error. This residual standard error is actually RSS. This one is RSS values. So these are the kind of 56,790 is the RSS, which means that this might be the sum of the residual error squares, which for the best fitting line for this. And then when we're looking at the coefficients, we will say the intercept is this one. So that means when the ground living area is 0 values, that's the basic kind of a sales prices, like a baseline sales price values. And then depending on the one unit increase of this value, gonna be increases on average, we can actually expect the increase of the sales price by $109.67 for every 1 square feet of the livable area increases. And then when we're looking at these t values actually calculates by in case of the 45.303, we can actually calculate by 109.667 divided by 2.421. This one actually gives you about the t values. And then as we know, these when we try to looking at the regression coefficients, our basic hypothesis is H0 is beta I equals 0. And then the alternative hypothesis is the beta I is not 0. So
Correct.
in this case, we have to use this kind of a t value is our coefficient is the 0 or not 0. So in this case, our p value is very small, which means we can reject the null hypothesis saying that beta 1 is 0. So that means we have a very, very low probability getting the no relationship between the variables to the outcome. So that means these are the very significant relationships. And then we also have R squares and the adjusted R squared depending on the weighted by the number of parameter. And then F statistic is a kind of a showing about the goodness of fit of the measures. So in this case, we have 2052 on 1 and 2, 2047 degree of freedom means maybe when we try to compare, the one actually means that we have a formula for the sales price and 1, which means it is only intercept model, okay? Which is also what is called the null model, okay? And then assuming that this formula is what we have a full model, actually, so we can compare these two F statistics, and then we can actually find calculate the difference between the difference in the F statistic value, like a chi-square values between null model and full model. And then when we calculate that difference, this one is the kind of a result in this case. And then under the 1 and 247 degree of the freedom, 2052 is the highly significant, which is the p-value like this. Actually, this one is the chi-square values for that represents about the difference in F value, F statistic value between null model and full model. Actually, we can assume that this one gonna be the full model in this case. That's the how LM summary look like. So is there any questions so far? Anything?
Just a couple of comments. Very good explanation. Okay. And one of the things that I learned when I was, starting, this journey in terms of linear regression is that usually that intercept that the LM gives you by default, when the variable the x is 0, okay, usually it's not, it doesn't match reality. For example, if you are dealing with housing units, you know that the gross living area is going to be greater than 0. Okay, if it's 0, basically there's no house, right? So unless there's some observations that is only land, vacant land. Okay, but discarding that scenario, what we can do is move, okay, the intercept, okay, move it maybe to a parameter that we can interpret. So we can move that intercept to, let's say, the mean of the gross living area, and then that will give you, a better understanding of when the guess is the mean value of the predictor. Then you will get that value from the y, from the intercept.
Yeah.
I had to look at my notes to see what is the mechanics to do it, but sometimes it's a more relevant number for the intercept that just when x is 0.
Yeah.
And you are right on the F statistic. Okay, it's also a hypothesis testing in terms of comparing the null model, okay, which is only the intercept. In other words, there's no predictors. Comparing the model with the intercept against the full model, okay, with the predictors. And usually, you know, I haven't seen this scenario yet, but usually the predictors, the full model or a partial model is going to be better than the, you know, that only the intercept, okay, because it's just a constant. It's just a constant.
Right.
Okay, but you know, there could be some, you know, weird cases that could fail. Okay.
Yeah.
But very good.
Yeah.
Very good.
Actually, this kind of intercept is what is called, in this case, is the baseline value. And then also, maybe depending on our research context or research objectives, maybe especially for some scientific journal, this intercept can be considered as what is called a status quo kind of values. Like when everything is controlled and then everything is kind of a very zero value before we setting up any experiments, what's the state quo value gonna be, and depending on the scenario. So you're saying it's a scenario. So that's the kind of thing. Actually, predictive purposes in here may, if we assuming that this one is the actually final full model, we can actually have a one single formula called sales price equal 15938.173 plus 109 plus 6.667 multiply ground living area. So by using this, based on these relationships, we can actually develop some of the predictive equations, and then we can actually estimate these sales prices as a predicted outcome variable. And then there is definitely error terms in here, right? And then when we try to sum of all of the error term, square of the error term, that actually gives us about the 56790. That's how this one goes. Actually, 56790 is quite a big value. So that means we still have a kind of a pretty big gap about when we predict the per sales prices. So that means maybe we have to thinking about we have to develop this one is much further than before. So by including more variables. So, and then when we're looking at the geoplot like this, and then we will see these kind of linear relationships. So that blue line is the best fitting line, right? Best fitting line with a small error term, like a 56790, like a minimum error term, right? So these are actually shows the best fitting line about the regression line based on all of these scatter plot kind of informations. So that is actually what the error variance is about. So maximum likelihood, which means minimize the square root mean square error, or mean square error should be, we have to minimize these values for these kind of error variances. So when we're looking at the summary at the top, that 56790 actually have error variances, and then this one is actually smallest kind of RMSE values, which means we have based on our single linear equations, that is the best fitting line for that. So that's the thing. And then when we move to the multiple linear regressions, multiple linear regression is very simple. Because before in the previous sections, when we predict the sales price, we only use the one single predictor, like a ground living area, right? But in linear regression, in multiple linear regression, we actually use the more than one predictor. So maybe 2 or 3 or 4 or whatever we have an independent variable like a predictors, we can include those things into the one model. So in here, this formula is the very, very basic general formula for the linear regression. So we actually include as many predictors as possible depending on our data set. And then there is also error term gonna be happen here. So in case of the model 2, maybe we can thinking about based on our current model 1, maybe we can adding year built variable, because maybe definitely year built gonna be highly associated with the increase and decrease of the sales price. So maybe the old building gonna be less sales price, for example. That is not always true, but yeah, it can be possible. So based on those kind of assumptions, we can actually get on some of the coefficients relationship like this. And then do you recognize these kind of parentheses like this? These are actually kind of a function for the print, just for your reference. So when you actually parenthesize like again to this kind of LM object, you can actually have a kind of a same function for the print model 2, and then that gives you this kind of a summary. It is not that detailed compared to the summary model 2, but it still have it still gives you the very good kind of a simple summary about what the regression coefficients is about kind of thing. But more detailed kind of information for the DEM model, you can always use the summary functions. And then when we looking at the bottom, the plot, this one is actually showing about what is the kind of a relationship between the year built and ground livable area, and then predicted value of the sales prices. So that means if we have a very small living area and then the years built is quite old, that means our predicted sales price is gonna be very, very low. So that means that those houses is a very cheap housing, right? And then when we go to the top right here, if we have a lot of buildable building square living area, and then we have a very brand newly built kind of housing, that means it is very expensive. But sometimes, depending on our scatter plot relationship, we also thinking about some kind of a two-way interaction effect, which is the multiply by living area to the year built. Because this one is actually saying that maybe depending on the time, maybe kind of a different kind of a design, housing supply demand, or maybe changing in depending on the number of families, single families. Because usually in the past, like a 1940 or 1950, during the baby boomer kind of a period, at that time, actually, single family member is pretty high, right? Because we at that time, people tends to have many children compared to the families in the 21st century, right? So that means we have to have some kind of a different housing demand, right? So to reflect these kind of things, maybe we can thinking about the intersect between these two, which means year built multiply by ground living area. So depending on the how old the building is, this living ground living area gonna be different. That actually produce the sum of these kind of curvy lines for the predicting our outcome. So that's the kind of what is called the intersection effect in here at the bottom. So basically in the book it says intersection occurs when the effects of the one predictor of the response depending on the values of the other predictors. So that means in this case, ground living area actually can be difference between the year built, and then that actually affects to the sales price like this. Okay, so that's the kind of what we have to use the intersection effects, and then to simplify these kind of things into the model, we always use that asterisk kind of a mark to simplify our formula, and then we have a single predictor relationship like this. At the same time, we have this kind of an interaction effect like this. Right? And then, is there any kind of question so far? Anything?
No, we're good.
Okay. So, and then actually when we looking at this livable area and then year built, this one is actually called the main effect, which means it actually represents the relationship between those variable and the response, the outcome variable, like a single one-to-one kind of relation. But this kind of interaction is what is called the interactions, definitely interaction effect. Like thinking about the interaction between the two predictors and the response variable. So and then here is the model 3 actually conclude all the possible main effects. Like we can conclude all of the 300 different possible variable, just dumping into all of the variable in this case. And even so, we can actually still have these kind of estimates and standard errors. And then when we move to go to the lattice, actually we have this kind of a t statistic, and then getting to the p values depending on these t statistics. So something is a very highly significant like this, and then the other is not. Yeah, we can still have these kind of things in the multiple regression. So that actually shows that if we have many predictors to include the model, we just feel free to include those model. But the thing is to optimize the predictive purposes, we have to keep trial error to get the optimized kind of situations that to get the best fit the regression model. Okay, so now we cover the types of the linear regressions. So it is very simple, only using the one predictors or maybe many predictors. That's the kind of yeah.
I have to. Let's tell you that it's already 8:02.
Oh, okay.
Okay,
all right.
but
yeah.
Excellent.
So maybe I think that let's wrap up today, and then I'm gonna try to explain rest of the section into that chapter, and then I think that okay, hold on, let's see. Let's see our presentations.
Right.
Yeah. Okay, hold on.
I could do the chapter 5.
Are you gonna do the chapter 5?
Yeah, there's no one, that
Yeah,
volunteer.
actually, chapter 5 is the Matteo Vega, like the person who attended our study group last week.
Okay.
He's supposed to do this. He actually
Okay.
wrote his name on it, but I'm gonna ask him again. And
Right.
then if he don't think he can do that, maybe you can do this.
Yeah. Yeah.
Okay? Yeah, I will keep you updated.
Okay. Excellent.
Okay, so this is it, and then yeah,
Mhm.
have a nice Sunday weekend, and then
You
we
too.
will we will meet together on next week.
Yep. Go with it.
Okay. Yeah. Bye
Okay.
bye. Take care.
Bye.
Yeah.